once we've worked through the algebraic details, which we've seen already, we end up with a delta y equal to 2at delta t plus b delta t plus a delta t squared, and we're going to divide that by our delta t. Delta t, of course, distributes, the division by delta t distributes, and we end up with 2at plus b plus a delta t. This expression tells us for any quadratic, as long as we know the values of a and b, and notice that the value of c doesn't matter a bit, as long as we know the values of a and b, we can determine, and also the starting time t and the delta t up to the next time. Okay, if we know t and delta t and the parameters a and b of the quadratic model, we can calculate the average rate of change between those two times, t and t plus delta t. If we want the instantaneous rate at clock time t, we just shrink the triangle down to nothing by letting delta t approach 0. As delta t approaches 0, a delta t is going to approach 0, so that term is going to simply disappear. Delta t doesn't affect 2at or b, so we're just left with 2at plus b. And we say that dy dt is the limit as delta t goes to 0 of this expression. We saw that the a delta t goes to 0, and we're left with 2at plus b. This is really neat. This gives us a uniform formula for the rate of change of any quadratic function. A universal formula that always works for a quadratic function. We'll be finding universal formulas for exponential functions, power functions, sine and cosine functions, and other trigonometric functions and other combinations of functions later on. But right now we have an expression that applies to any quadratic function. And this is very powerful and very neat, as we'll see. There's a lot of things you can do with this.